everybody. I'm pumped up today. I actually have found and sort of proved a function that actually counts the ith rational number. And just to be sure we're clear on what I'm talking about, this is the famous proof by George Cantor, where he lists the rational numbers with some redundancy, quite a bit of redundancy. Like notice this bottom row is 1 over 1, 2 over 1, 3 over 1, 4 over 1. And he does the very same thing, except it's all the fractions with denominator of half, all the fractions with denominator third. And he came up with this neat way, I guess it's kind of a diagonal approach. Some people just call it zigzag, where you can count your way through here. Like 1 over 1 would be the first rational number, it's just an integer. 2 over 1 would be the second rational number, still just an integer. But the third rational number would be 1/2. Okay, and so that's what this function actually does. This would be I equals 1, I equals 2, I equals 3, I equals 4, I equals 5, and so on. And you continue in this zigzag diagonal fashion. So again, let's go up and take a look at the function again. Now, it's a little messy, but it works out okay. It actually involves, and this has to do with triangular numbers, believe it or not. If you recognize these pieces right here, that's kind of the triangular number result with a minus sign in there. But anyway, this is a ceiling function, what you call a ceiling function. And there's a quadratic that gets solved in the middle of the proof, and you end up with this strange looking result where this occurrence of C that you see 1, 2, 3, 4, 5 times here is computed by this ceiling function. Okay, now I'm gonna go through some concrete examples to make sure it makes sense. But again, the ceiling occurs a lot, and then the actual index itself is present twice. Now I could have simplified this algebraically. I didn't see any. It's kind of the result of a proof, and so I just left it the way it was. You can do the computations go okay, but let's go down and see how a particular computation might go. Now, so Q at 3 means to find the third rational number. Now, the first thing you have to do though is find the floor at 3. Now, this one turns out to be easy to compute, because you see right here, this radicand would be 25, right? So the square root of 25 is 5, all right? And then the square root of 25 is 5. If you add -1 to that, you get 4. If you divide by 2, you get 2. Now the floor, just like the ceiling of a natural number, is just a natural number back. So nothing really happened there. As long as it's not a fraction, it's just going to return the value. So we do get that this important ceiling function returns a value of 2. And if you look here, if you put a 2 everywhere, you're supposed to. And again, you're just putting a 2 everywhere you see a C right here. That's 1, 2, 3, 4, 5 occurrences of C. And so that's exactly what happened right here. You see, we took this 2 that we computed, put it here, 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 here. Just all over the place. All right. Now, and then you get 1/2, and like so you see Q at 3. Q at 3, you see right here, corresponds to this first, second, third position here. All right. Now, let's do one slightly more challenging. Let's go ahead and do it. Let's see if we can find the 17th. All right. Let's see if we can find the 17th number in that grid. Now, this one's a little more challenging. This resolves 8 times 17, I think, is 136. So you get the square root of 137, which is a number between 11 and 12, right? Because 12 squared would be 144. So this would be a number between 11 and 12. If you subtract 1 from that, you get a number between 10 and 11. But if you divide that by 2, you get something around 5.5. Okay, but this is the ceiling, so we elevate that to 6, right? This is the ceiling function, so we elevate that to 6. And you guys can go through and verify that calculation. And notice that now the 6 is what occurs all over the place. 6, 6, 6, 6. It came from this computation. To me, it would have been messy to leave this in the middle of this formula. That's why I broke it apart like this. Okay, and again, if you run through the calculations, you will get 5 over 2. Okay, now remember, what does this 5 over 2 represent? It represents the 17th position in this diagonal sort of zigzag. So let's count up here, okay? All right, so let me make sure this is on the screen. So we're saying that the 17th rational number in this enumeration is 5/2, right? The 17th rational number in the enumeration up here is 5/2. So let's count and see what happens here. So let's just follow along here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now you keep going up. 9, 10, right? 11, 12, 13, 14, 15, 16. That's really 6 over 0 right there. So this would be 16, 17, folks, right there. 17, 5 over 2, 5 over 2, right? And that's what we got. So hopefully you have confidence in this calculation. It's really cool. The proof isn't that bad. A number of people on the web that I've wanted to see this, an injective function and all of this, but this gives you a function that goes by the index of the location in that grid. Now, just a few comments. You guys can do this, but you can show that Q at 1, the first rational number, is equal to the 5th rational number. So you get 1 over 1 is equal to 2 over 2. And again, let's go up. Here's the first rational number, the second rational number, the third rational number, the fourth rational number, the 5th, right? 1 over 1, 2 over 2, right? So they are equal to each other. They are equal to each other. So the mapping is definitely not 1-to-1. And I believe it is a surjection. I think it's an onto function. But anyway, more to come on this. I may produce a proof at some point. Hope you guys enjoy.